Thank you. Thank you, everyone, for being here. So who's happy with Scala compilation times? Let's just get these people out of the door so that we can get started. All right, so who I am, very briefly, co-founder of Triplequote. We started about a year ago. And before that, I've been working on several open source projects in the Scala ecosystem. Among those, I've been I've been working for quite a while on the Clip Scala IDE. So I definitely have some good experience with tooling in the Scala ecosystem. And I'm also the author of the Scala Migration Manager. So this tool for checking binary compatibilities across releases of your library. So this is our mission at Triplequote. We want to help you cut down on sword fights in the Scala community. So have you ever felt like this guy? We're all here because we love Scala, right? You feel so much productive with the language, but have you ever spent any time considering, how much of those productiveness that you feel is actually wasted by the time you wait for the compiler to get back to you? So, right. So I can definitely relate to him. I definitely feel the same, despite I love the language, but I can definitely relate to that, and I am hoping that all of you actually feel the same. So what can we do about it? Well, we can go and sort of build sophisticated technology so that, we can get pulled back to work when compilation is done. That's definitely one way to do it. But of course, we think we can do better than that. So let's actually have a look at what we can do. So the agenda for today is we'll start by looking at the state of Scala releases, trying to answer the question, is Scala getting any faster? And what does that mean for us? Then after that, I'll sort of start, bothering you with things that we can do today to sort of challenge and question the Scala compiler. Because right now, you have a project, it takes X minutes to compile, you just accept that, right? You never try to challenge that. So I think we should stop bowing to the compiler and actually do something about it when things are not as fast as we expect. And at the end, I will also talk about Hydra. So this is a product we're working on, and I'll tell you a lot about it, so that I would say there is salvation from long Scala compilation times, and Hydra can help with that. But it's not the only tool, so we should know what is available today already. So what about Scala releases? Scala 2.12 was released a year ago, actually, exactly 1 year ago. And the biggest thing that it brought from my perspective is that it targets Java 8. So it actually took advantage of all these features that are available in the JVM for Java 8, right? So what are these features? Well, one is that instead of compiling traits in a, I would say, fairly complicated way, now they can actually be compiled to interfaces with default methods, of course, if you don't have state. But anyway, you take advantage of Java interfaces, and that actually helps you reduce the binary footprint of your libraries and your own class files. But that's not the only change. Also lambdas, the encoding for lambdas was changed. So instead of creating a class file for every lambda you define, it's actually being encoded just like in Java 8. So it's a static method in your class file. So it's a lot more effective from a memory footprint perspective, right? But what can we say about compilation times? Well, talking to Miles, he wasn't quite happy with Scala 2.12 initial compile times. And in fact, shapeless tests were taking more than 20% to compile with respect to 2.11. So there was a regression according to him. But if you were talking to the Scala team, they were actually quite pleased. They said, well, it seems to be about the same, maybe a little bit better. So the big realization, the Scala team knew already, was that, well, it's hard to assess whether new releases of Scala were getting any faster up until 2.12. So they had to do something about it. And what they did is actually they created automatic benchmarking for, they automatized the process of benchmarking and basically spotting regression in compilation time so that they could prevent those regression to get merged into master. Or if they get merged, well, they have a way to actually spot them and fix them. And that actually brought us to 2.12.2 that was released a few months ago. and has brought quite a nice improvement in compilation times. According to them, again, it was something between 20 and 30%, but that's also what I've been hearing from people. Moving from Scala 212 something to Scala 212 2, they got about a 20-30% boost, which is an impressive result. I mean, 30% compilation improvement is just great. I mean, you would like to get that every time for every release. Eventually compiling Scala would be just as fast as Java, if that was possible. And the other news is that actually 2.12.4 also seemed to be a little bit better than 2.12.3. You know, again, I don't have enough data points, but according to the Scala team benchmarks, they also got a little bit more performance, something like maybe 5%. So they actually got a bit better. But the question is, so the Scala team is working on performance, and we have evidence of that. What does that mean for us? Is that like sort of a done problem? We don't have to look at it. We don't have to care about compilation times because the Scala team is doing it. So they're going to solve the problem for us. Of course not. We can do still plenty of stupid things in our code, or you know, maybe they're not stupid, but we abuse maybe some feature, like we start writing a lot of macros. Macros can take a lot of time to compile. And you know, that's how you get to feel the pain of long compilation times, right? So of course, the fact that the Scala compiler, well, the Scala team is working on that is not enough. We still need to do our work. So what can we do? Well, as I said at the beginning, I think we really need to stop bowing to the Scala compiler. Like, you know, start challenging your compilation times. Don't accept them blindly just because you see the Scala compiler as a black box. I know it is a black box. But there are things you can do to actually unveil some of the details and get an understanding of what's happening and whether there might be some inefficiency that is caused by, you know, your code patterns, things that you are doing in your code. And that's what we're going to talk about now. So what are the existing tools that we can use to understand if we have a compile time inefficiency? So the Scala compiler is your best friend at this task. It has a ton of compiler options. I don't know if you've been exploring them, but you know, if you do Scala C minus Y, well, you get a ton of options. Also, if you do Scala C minus X, and that's on top of what you get when you do just Scala C minus help. So there are a ton of options to explore, and I would say there are some that can really help you right away. You don't have to do anything. You just need to enable them, maybe on your CI, and they spot basically a use code, right? And of course, if the compiler has to do less, it will be faster. So I would say usually you shouldn't expect, you know, 30% speed up out of enabling these minus Y warn flags, unless you really have a lot of that code. But I think it's a good practice, and probably it's okay to pay the price of, you know, of course those flags do things, so you get a little bit of an overhead. So I wouldn't maybe enable them for all developers while, you know, you're in your development time, but I would probably do it on the CI, or at least on a nightly build, so that I get the information that every morning I can have a look at that and see if there is anything that you know, we can fix to improve our compile time. But as I said, probably those will not bring you those like 30% speed up, and if you're really feeling the pain, then that's when you really need to start sort of digging into the compiler. Kind of, you have to be willing to understand how, you know, how deep the rabbit hole goes. So, and for that, actually, you can be sort of pragmatic. There is an approach you can follow. So you should start by using minus verbose. So verbose gives you a ton of information that you don't care about, but there is actually one bit that is extremely relevant. It gives you the time per phase, so the compilation time per phase. So as you might know, the Scala compiler has many phases, actually 24. And minus verbose gives you, okay, my sources, how much time they took to compile for each of those phases in the compiler. And I'll tell you in a moment why this is interesting. What are the phases that you want to look at? Minus X print, and then the name of the phase gives you the abstract syntax tree, so the representation of the compiler of your code after a given phase. So again, this is interesting because, well, as you know, there are many things in your Scala code that you don't see, but they exist, right? It could be implicits, it could be macros. So those are things that are not visible in our code, but that the compiler has to somehow generate in our code. And of course, for this sort of generation, well, it needs time. So by looking at the AST, you can get a feeling, okay, how much of that code is being generated? And in my experience, like I've seen source files where we had like maybe 200, 300 lines of code that would take, I don't know, 60 seconds to compile. And it was kind of weird. And then you actually look at the AST and you see that there are 50,000 lines of code. And so you kind of get the idea where that, that minute went during compilation. -x log implicits is to understand what are the implicits that the compiler has attempted, but they didn't work. Of course, the more implicits the compiler has to check, the more time it will take for compiling. And last but not least, there are some -y macro flags that are useful for debugging, what happens during macro expansions. So those are, to me, and in my experience, the flags that are the most useful when you want to go and understand where your compile time is spent, and also detect those inefficiencies. So how do you get started? As I said, you start by using -verbose. So -verbose gives you a ton of things, but what you get is the time per compilation phase. That's really why this is useful for us. So here, we just put a graph where we have the phases and the compile time for two projects. One is the Akka actor module, and another one is a project at Zalando we've been working with. So the thing that should be striking you is a green bar happening for the Zalando project, which is not happening for the Akka actor module. So that's, in case you're wondering, that phase is type checking. It's typer. So it's not something that, it shouldn't be shocking that typer takes time. But in that case, typer was taking more than 50% of the whole compile time. So it was definitely too much. And I would say that when your project takes more than 50%, well, to me, it takes more than 40% or even more than 30% in the type checking phase, you should at least know why. If you have a good reason for why, if you understand why it takes so long, it's fine. If you don't, then I think it's your opportunity to learn something about your project and potentially discover there is some inefficiency. And the good thing about this is that probably when you find out about a problem, that problem is probably propagated across the whole project. So by actually fixing a problem, you're probably fixing a lot of your compile time problems. And that's what happened at Zalando. So I'll tell you a bit more later on, but that's exactly what happened at Zalando. So you need to investigate. So what are the usual suspects for long compilation times? Well, there are macros, which our ecosystem is depending on more and more. Implicits, and even more when implicits are implemented through a macro. And the other one that could be surprising is also type inference can play a role. So there was actually an interesting tweet that adding explicit types in the IntelliJ Scala code base led to almost 20% speed up in compilation time. So I was actually impressed that it was so relevant. I don't think that's the case for every project out there, but maybe you should try out adding explicit types. Maybe you should use Scala fix to automatize the process and actually see if it makes sense. So if you see a huge benefit, then then maybe you're okay to pay the price of a little bit more verbosity for less compilation time, or maybe not. It's your decision. But all I'm saying is that it might be playing a role. So how do you investigate? The real problem is that where do you focus your attention on? Where do you start? So it takes a lot of time to compile. Okay, but what do you do next? Ideally, you should identify a source file from where to start your inspection. So you should know, this foo file is actually taking 5 seconds to compile, and I think that's too much. Why is it taking so much? So I start digging into that file. So that's what I mean by, you need, at this point, the tooling doesn't really help you with that, so you need to have a guess for it. So where do you think you might have a compile time inefficiency? And once you identify that source file, test your assumption. So how do you test it? Compile that single source file alone and see actually what is the compilation time for that single source file. And you can do that with the Scala compiler. For instance, a simple way is that if you're using SBT or any other build tool, you extract all your class, but all the compiler options that SBT is using for compiling your project, and then you do it from the command line by passing the target folder, so that the only source that you compile is the one that you want to compile, and everything else is actually available to the compiler as class files, so that the symbols are loaded from the class files, and so the only source that you compile is the one that you want to compile. So once you tested your guess, and you indeed find out that yes, it is quite slow, and I don't understand why, then start inspecting the AST. Most likely, it's because macros and implicits are at play. So the AST, it will tell you if macros are, if there are macro expansions happening in that source file, and is this something you expected or not? What are the macro expansions that are happening? For instance, do you expect that a value is computed through a macro expansion, or maybe did you expect that it was available in the implicit, like it was available through some other, through an implicit that it should be in the scope, but it's not, because it's being computed with a macro. So those are the things that you need to look at in your AST. And another one is there any complex inferred type? Since before I mentioned that inferred types can play a role, that's another thing that you can see in the AST. You can actually see what are all the types in your program, in your source file. And actually, if neither of those are there, then I would say it's, I don't see another option. It must be implicits at play. If you have some other idea of what could be, please, speak up. But I don't see it. Like, it must be implicits. So the compiler is spending time trying to find the implicits for compiling that, your source file. So since we talked about implicits, do you know how implicit resolution works in Scala? Yeah? Everyone feels confident about it? Okay, well, I was going to suggest that maybe we should take a break, like 5 minutes. We're going to have someone dancing, apparently, while we take a break. And just read chapter 7 in the Scala reference. Of course, we're not going to do that. But one thing I do want to point out is that in Scala, when you don't know something or you're not sure about the behavior of something, have a look at the Scala reference. It's very readable. It's not full of Greek letters or things that could be comprehended only by doctors. I'm not a doctor, so I can still read it. So I would definitely encourage you, whenever you have a doubt about something, whether it's implicit resolution, trait linearization, anything else in the Scala language, have a look at the Scala reference. It's short and sweet, and I really think it can help. But for the ones that are not sure about how implicit resolution works, let's build an understanding. So we have some really stupid code here. We're calling a method show with an employee value, and the method takes a map. Of course, you should never do that. But if you do that, the compiler, what will it do, the compiler? So this expression will not fail right away, right? The compiler will say, well, okay, employee is not a map of ID employee, but maybe I can fix that. Maybe I can heal that code. And so the first thing that it will do is that I will look into my current scope and see if there is an implicit conversion from employee to map of ID employee, right? If I can find that, well, I just apply the conversion and move on, because the code now compiles. So far, so good, right? But what happens if the implicit conversion is not available in the current scope?
It looks in all of the scopes that are necessary for implicit search.
Right, and what are those? Like, there is a name for that. So if it's not available in the current scope, the compiler will look into what is referred to as the implicit scope. And the implicit scope, usually, it just means it looks into the companion objects of all of the types that are involved to see if there is an implicit conversion, well, from the, your type to the expected type. So let's see this graphically. So this was what happens at the beginning. So this is the current scope. The compiler would just look into, your imports, your package object, your local definition. Is there an implicit conversion from employee to map of ID employee? If I cannot find it, then I start looking into the implicit scope. So what is the implicit scope? Well, in this case, we have 3 types involved. We have map, ID, and employee. Those are the 3 types. And I will look into the companion object of these 3 types as a first thing. But that's not it, because map is a compound type, right? So I will not just look at the companion object of map, but I will also look into, I will also look into the companion object of seek and iterable, and so on, because maybe seek implements or extends some other type, and iterable the same, and so on. And so you can see that basically the compiler will do quite a bit of work here, because that really depends how many implicits do you have in scope. Just imagine, for instance, I know like in Scala or cats, what do? You do an implicit import, then some namespace dot underscore, right? That's not the case. I know that's the case in Scala Z.
It is the case. You shouldn't do that.
Okay.
Exactly the reason you're about to
Okay, good. I've seen enough code doing that. Thanks, Daniel. So people do that apparently in the wild. And what happens in that case is that you may be importing a lot of implicits into this scope. And the problem is that maybe the implicit you need is actually in the implicit scope. Is not available here, but the compiler will still have to go and evaluate those implicits and understand whether there is one that fits for the code that is trying to heal. So all this is just to say, yes, implicit resolution can be costly. So you shouldn't be surprised if, after your analysis, it turns out that implicit resolution is what is slowing down your compile times. So as I was saying, one obvious tip is try to avoid imports, wildcard imports, because you have no control over those imports. Maybe today there is no implicit defined, but tomorrow there might be. I would also say avoid defining implicits in the package object, if you can, for exactly the same reason, because those implicits are available across all the classes in that same project, right? And so where should you put your implicits? Try to put it in the implicit scope as much as possible. Of course, it's not always possible, because maybe you don't have access to some type. But whenever it's your type, well, you have control on that, so try to put your implicits in the implicit scope, so in the companion object. And that's actually a very good thing to do, because anyway, the compiler knows where to look. It will be looking at that. So also for the user, it doesn't have to remember to import anything. It will just look into the implicit scope, and so it will look into the companion object. And to sort of bring it back to the initial graph when I show you this project at Zalando, that it was taking more than 50% just during type checking. Well, for them, it turned out that they had an implicit defined in a package object. That implicit was computed with a macro, okay? But what was interesting is that that implicit was computed every time the value was needed, even though a value was already available in the companion object. But the problem is that this macro in the companion object was being inspected before the implicit scope, right? So basically, this macro was being triggered, and compilation time was being spent there every time for many, many sources. And while there was a value that was good in the implicit scope. So the trick there was just, okay, let's just make sure that that macro doesn't get kicked in, because we already have a value that is good. And that actually delivered a 40% compile time improvement on their project, just by doing that. Of course, it took a day of analysis, but the benefits were huge also because that single change was actually had an effect across the whole code base because they were using those implicits quite a bit and they had similar patterns in other places. So if you find that interesting, they also wrote a case study, so you can actually find out about the work we've done there, and getting a little bit more details about the problem and the solution. So let's now talk about macros. Macros are great. I mean, I like them a lot. Of course, they allow us to write less code, so we can get rid of a lot of boilerplate. But macros can also be quite expensive. So there are times when they can be responsible for 80–90% of your type checking time. So my word of advice would be try to be pragmatic. So if there are places where you're really getting benefits from using macros, sure, go ahead. You're aware of the cost of them. So again, it's always trade-offs. But but maybe there are times when it's just better to maintain a little bit of boilerplate instead of having that that time being imposed on you and your team at every compile, on every day, on every CI build, and so on. Yes.
So I have a question about that because this is actually new to me. I wasn't aware that macros intrinsically impose a cost. So are you referring to macros that are themselves expensive to run or generate large trees, or just like actually having a macro triggers significant inefficiencies?
So
even a very small macro.
Right. Well, a macro has to be type checked, and if you look at the compiler, it actually gets type checked, I believe, 3 times. So you can see that depending on the macro, the cost could be quite imposing. It really depends then on what the macro does, of course. Okay. But I remember looking at like silly things like quasi quotes. There was actually a file in specs2 that contain quite a few quasi quotes that are implemented with macros, quasi quotes. And what was interesting was that it was always generating sort of the same tree. It had like different arguments, but it was more or less always the same thing. And it was taking, I don't know if it was 3 or 4 seconds to compile that single source file. But you could actually move all these calls to quasi quotes to a single place, so that it would only be triggered once, and then your compilation time went from like 3–4 seconds to half a second.
So I guess maybe a better example then, because like quasi-quotes is already doing ridiculous things, right? So maybe a better example would be a simpler string interpolator, like a string context S.
Also, string interpolation have a cost.
Really?
Yes.
So is that significant?
I mean, it's significant the moment you have enough of them, of course. But they give you readability, so of course I like to use them as well. Yeah. But yeah, sometimes when I see that the value has to be added either at the beginning or at the end, I actually just go with plus and the concatenation syntax just to avoid that. And the other thing is that usually you don't feel too much of the pain because it's such a small change, it's such an incremental small change. But the problem is when you look at the project as a whole, and that's when you're going to feel some pain. So, if you think this is art, I agree with you. This is definitely not something that it's simple to do, but I think we need ourselves to get into this habit that we start questioning what the compiler does, we start challenging it, and we also start understanding what it does. So it's not a black box anymore, but we start looking into it. And, I think from this realization, actually, we're trying to do something about it. So as a Triplequote, we're doing things, but also the Scala Center is doing things. So actually, the fact that we all agree there is a problem, it's quite interesting because I believe the future looks a lot more brighter than it is now. So I'll now switch and talk about Hydra. This Hydra is the product we're working at Triplequote, and of course, it's related to compilation times, and it's also very much related to what I just told you. So all these analyses that you could do manually. So the idea with Hydra was to build something that, sort of 3 pillars. We want it to be distributed, so it would basically scale up and out compilation. So it's all really about compilation. We want to use those machines that we have right now that have many, many cores, And potentially, we also want to distribute to the cloud, since now, the cloud isn't really, it's pretty cheap, so we can actually use those machines and try to get faster compile times. Then we want it to be transparent. So Hydra should really just meet you where you are. You shouldn't need to change anything. And last but not least, we want it to be insightful. So meaning that all these things that I told you about, you shouldn't need to do it. The tool can do it for you. It can do it much better. You don't have to waste a day. So it can just help you. So at the beginning, it can just help you identify those problems, but ideally, it could also just lead you to the solution instead of you having to do the work. So, but before we get to the metrics, let's start talking about distribution. So distributing compilation, it's, I would say, quite a natural idea. Probably everyone thought about it. So what are the challenges with that? So one of the challenges is interfile dependencies. So the problem is that sometimes you can have sources that depend on each other, but they may end up being compiled by different workers. So this, of course, it's a challenge. And the other one is that, well, if you go distributed, you're building a distributed system, and that's not a simple task. So there is complexity on building a distributed system. So if we embark on this journey, let's see what are the benefits that we can opt for. I'm sure that you guys all know Amdahl's Law, which helps us get an understanding of what is the speed up that we can obtain from parallelizing some work, or from parallelizing an algorithm. So P is the percentage of work that is parallelizable. Ideally, it should be as close as 1. And S is the speed up. So it's, in our case, it's basically the number of cores, right? So just to do an example, let's say that S is, well, let's say that P is 1. So we have an algorithm that is perfectly parallelizable, and S is 5. Then what you expect is a 5 times speed up, right? It's linear. The more cores you add, the more speed up you get. That's the ideal scenario. In reality, having an algorithm or an implementation that is fully parallelizable is a dream. I think I still need to find one if it's not a trivial problem. So what you'd really want is actually trying to get P as close as 1. And the other one is that S is, of course, not infinite. So we know that machines have a fixed number of cores. So let's see what are basically the speedups that we could obtain from parallelizing compilation. And let's start by assuming that S is infinite. So this is what we could obtain. So if we have an algorithm that is perfectly parallelizable, then we can have infinite speedup, right? 0% is the amount of work that is not parallelizable. So we have something that is fully parallelizable. We can get infinite speedup. But just imagine that we have 10% that is non-parallelizable. Then suddenly we go from infinite to 10 times speed up. That's quite a drop, right? And of course, this decreases not linearly. So if we get like 20% that is not parallelizable, then suddenly we have at most a 5 times speed up. And so what are these things that are sort of non-parallelizable? Well, in our case, it's everything that happens on these different workers that try to compile. So JIT compilation might be happening, memory bus contention, and then again, interfile penalties, because you might want to get some information from a source file that you don't need to compile. So getting those information could be costly or could cost you some time. But of course, the number of cores is not infinite. So let's actually see what are the realistic numbers with our machines. So if we have 4 cores and 8 cores, and here I highlight basically what is the zone that we are aiming at with Hydra. So with 4 cores, we can see that we can get, well, between 2 and 3x speed up if we have something that is not, if the compilation is not parallelizable between 10 and 30%. Well, if we have 8 cores, then the speed up actually gets quite nicely. So it gets between 2.5 and almost 5 times speed up. So those are, this is just to put things in perspective. So these are the numbers that I think we can hope to get from parallelizing compilation, from parallelizing Scala compilation. So where is Hydra today? Well, we didn't build yet the distributed part of it, so we don't scale out, we scale up. We use all the cores that you have available on modern hardware. And the idea is that we really parallelize the old compilation pipeline. So all phases are being parallelized, and the image hopefully helps you picturing what happens behind the curtains. So you have your Scala sources, then there is this component, this Hydra, that takes your sources, and it basically splits them in an intelligent way and assigns them to the different workers. So there can be 2, 3, 4, X, depending on how many cores you have. And so those different workers are going to compile in parallel a subset of your sources and produce class value, just like the compiler does. So the problems with parallelizing the Scala compiler are, well, again, interfile dependencies always come back and hit you the moment you want to parallelize. But the other one is really that the Scala compiler is built with laziness and mutability inside it. So the way we started was an approach where we had a shared nothing approach. So, because its mutability is bad, so you need to control it. So the easiest way was, okay, let's just, share nothing and redo a lot of the work. But of course, that doesn't really bring you that far because you redo too much of the work. So I would say the secret sauce with Hydra was in adding back controlled state, so that, adding back mutable state in a controlled fashion. So that's actually how you get speed ups out of it. So how well does it work? So here we have the Scala, vanilla Scala, and it's the baseline, so that's why it's 100% always. And then you have, Hydra, it's the red bar, and it's in relative terms to the baseline, to vanilla Scala. So you can see, depending on the project, so these are like specs2 modules, and then we have shapeless modules. Depending on the project, the speed up is different. So it's always the same machine. We have used the same machine. It's a Xeon, quite a nice machine. I mean, it's a Xeon E5 with many, many, many cores. We only use 4 of them. But as you can see, the speed up are actually quite interesting. You get from like 1.8 to up to 3 and something. And so these, of course, so the speed ups are different because it depends on the project. So there are some projects that are, you can parallelize better, and some projects that you can parallelize, less better. Why? Well, usually because there are interfile dependencies, and so you need to recompute more information on some project than on other. Another thing that you'll spot is that for test, we work much better than for main sources. Also, that is pretty expected. Why? Well, because tests have less interfile dependencies, again. So interfile dependencies are a challenge, and we're very aware of that. And we have ideas for actually bringing also the compilation of main sources, close to the level of test sources. But I think it's already quite impressive that, by not doing anything, you can actually get almost a 50% speed up on your main sources. And this is done with Scala 2.12.3, just in case. Yes? No, let's, if you want, we can talk about the type level compiler maybe at the end. Okay. And so this is like, just comparing vanilla Scala to Hydra. And here we have a graph comparing vanilla Scala to Hydra, but also kind of comparing the cold compiled performance versus the warm compiled performance. And cold compiled actually matters for your CI. Right? So Hydra, it's the red line. And you can see that Hydra actually outperforms vanilla Scala on cold compilation. And it's actually faster than vanilla Scala when it's warm in this project. Again, every time it depends on the project. It might depend on the machine. But, that's what we're seeing on several projects, that actually the cold compile times for Hydra, they're usually better than the warm compile times for vanilla Scala. So, and last but not least, insights. So this is the part where, everything I told you before, we want to actually automate is we want to make it automatic. We want Hydra to display those information to you. You'll have it available in a nice UI. Eventually, maybe in the CI, it will run for every of your compilation times, and you can just profit for understanding if there is any problem, and then eventually also it will contain the intelligence to solve these problems. So this is really our future, where we want to go with Hydra. So it's not just going to be about compiling faster, it's also about understanding why your compilation may not be as fast as it should be and what you can do about it. And last but not least, it's transparent. So this is what I told you before. So if you want to use Hydra, what do you need to do? Let's say you have an SBT project, that's what you have to do. You add an SBT plugin, SBT Hydra, and that's it. You keep running compile as usual, and what will happen is that behind the scene, instead of using the vanilla Scala compiler, it will use Hydra. So what do we support today? We have support for any release after 2.11.8, so 2.11.8 plus and 2.12.1 plus. And Scala.js is supported. We have lots of prospects that are using Scala.js with Hydra today, so that's definitely something we support. We have SBT, Maven, and CLI as ways to use Hydra. And Gradle support will also come. So if you're interested on that, express your interest. Of course, we'll prioritize accordingly. And last but not least, we're building the IntelliJ support. So IntelliJ is already supported. Why? Because you can build or you can compile through SBT in IntelliJ, or through Maven, or through these other build tools. But in IntelliJ, you can also compile inside IntelliJ with IntelliJ Builder. And so this is what we are doing, and the IntelliJ team is aware of that. And in fact, it's going to be, like Hydra will be bundled together with the next IntelliJ release. If I have time, I'll show you what we have so that you get a feeling. And thanks, everyone, for your attention. If you're interested in joining the early access, yes, so Hydra is currently in early access. It will still be a few months before its general availability. That's the URL to follow in case you're interested or your company is interested. So I can stop here, get your question, or I can show you a couple of things. So the two things that I have to show you is, one is the IntelliJ integration, really quick. And the other is the metrics that we already have in Hydra, so that you get a feeling of what it can do for you. Any preference? I didn't. Zinc? Yeah, Hydra works with SBT 013, so I didn't put that. 013 and 10. So it actually supports, the old and new incremental compiler. In fact, when you incrementally compile inside Hydra, inside SBT, inside IntelliJ, because also IntelliJ uses Zinc, inside Maven, you're incrementally compiling with Hydra. So the incremental compiler just okay, what are the files that I need to recompile? And then it delegates, to the compiler. In our case, it will be Hydra to run the compilation task. So you're profiting from parallelization, not just during a full build, but also during an incremental build, if that was the question. Yeah, okay. Yes, just Daniel, before I get the question about type level, and then I'll get to you. What was it again?
I was wondering if you tried to compare Hydra with type level Scala, or if Hydra could be used with type level.
Good. Thank you for the question. So the question is if Hydra can be used with the type level compiler, and if we did any comparison between the two. So Hydra, at the moment, is a compiler fork. So it's a fork of the Scala compiler. In the long run, we actually want to make it so that, we modified a few phases. So we can actually, since the compiler is, a sort of a, well, there are many phases and you can swap phases. We want to make it so that we're, just adding our phases or swapping our phases so that in the long run, it will be usable with the type level compiler. But as of today, it's not, because it's a compiler fork. So we fork the Scala compiler and not the type level one. But there is nothing that would, prevent us from supporting the type level compiler as well. as things stand at the moment, it's just really a matter of time and persons. And I know that Daniel is interested on that as well. Okay, Daniel, you had a question?
Yes, my question was, one of the largest costs of implicit search, right, is sort of falsifying all the numerous branches that it has to go through. I would assume you parallelize that, but in the process of parallelizing it, do you also cache falsifications and things like that across branches?
So yeah, those are good points. So at the moment, we're not doing that kind of optimization. But those are definitely things that they're on our backlog. There are things that we believe we can do right away that would yield more benefits, maybe than that. But again, it's hard to actually estimate what are the benefits. You need to do some R&D and get some project and actually compare numbers and see whether the approach is yielding more benefits than the cost, because that's the other thing. The moment you start modifying those, I would say, peculiar parts of the Scala compiler, there are two challenges. One is that you want to make sure that you're not changing the specification, and the specification is the current implementation of the Scala compiler. And the other one is that the changes you do, they're worth because you're left to maintain them. So every time there is a new Scala release, we get out with a new Hydra release. So it's always like you need to be sure that basically the changes are worth the cost. But yeah, it's a good point, and there are many ideas that we have that we need to explore. Yes.
Actually, two questions from me. The first one is, people will hate me for that, but we do not have problems with compilation time.
Okay.
Relatively, yeah. I did want to answer your first question, not to just keep but our CI pipeline runs inside Docker containers, and the most time is taken by the Hydra resolution.
Yeah.
Instead of,
So basically saying that dependency resolution is at the moment is more of a pain in their team, in their project than compile times. I understand. My first reaction would be, are you using Coursier? If not,
we tried.
If not, I would.
We went back.
Yeah, but maybe try again because it's moving fast. So it depends. How many months did you try that?
Just put Spark and Elasticsearch dependencies into one project. You are screwed up.
So we actually do this.
Okay.
And the reason that it's screwed up is because Spark's build is broken, and Spark publishes 3 conflicting versions of Netty.
Okay.
You can fix this problem. I can show you how to do it. It's in an open source project.
Good. Maybe you guys can take it offline.
Coursier is the right answer. Ivy is just buggy.
Okay.
So.
Good. Yeah. No.
And
I'll be there.
the second from me, so I remember there was a talk from Martin. Actually, he was describing that, how do they try to optimize the whole process? Like he explained that.
You talk about Dotti in this case, or are you talking about Martin Odersky and Dotti, or?
I remember it was about Dotti in general, but he described the problems with the current process, and they had this whole pipeline of steps of the compilation steps, and he explained that actually each step is that optimized that there is no space to optimize it further. At least I remember it from that talk. So what's the black magic here?
that we use all the cores. That's the magic, and that's the main difference. Dotti at the moment and the Scala compiler, they do single-threaded compilation. So the magic here is really okay. We have machines that have 4 cores, 8 cores, and actually look at the i9 specification. We'll have even more cores very soon. So the idea is really, they told you the free lunch is over. We're telling you the free lunch is actually, we got back the free lunch. So.
Just put .var into the code, right?
Yeah, pretty much. That's what we're doing. Yes. I don't know if we still have time. Someone has to tell me if we need to break it.
8 minutes over your head.
2 minutes left. Okay.
So I have just one question and one feedback to share. My question is you recommended moving implicit definitions from the current scope to the implicit scope.
Yes.
My question is whether, if you import, for example, just very specific implicit instance, and so there is no potential conflict or namespace to grows, isn't grows the linearization of every related type?
It could be, but you need to it could be. Of course, there can be cases where it can be faster, but you need to test it. I cannot give you a straight answer to the question. But I would say the good practice to me is avoid wildcards. And then if you have a good reason for doing it and you know what you're doing, of course I'm not gonna say it's bad. But if the default is I always do a wildcard, I think that's bad.
My feedback is actually because I've also been using the Hydra compiler in the early access program.
Yes.
Apart from the speed up you may or may not get for the project, the real amazing thing is the metrics.
Right. Yeah.
Because just as an example,
I wanted to show that. So.
I really managed to get a compilation time for a module from 1 minute to 5 seconds.
Right. Yeah. Right.
Surely some in this distance were missing because someone forgot to make them implicit, and the macro extension was happening all over and over again.
Yeah. Thanks for mentioning that. And yes, in fact, at the beginning I said you have to have a guess for where the problem might be. Well, Hydra at the moment gives you this. Every time you compile, you have this file, and it gives you a breakdown by compilation unit of how much time it takes to compile. This is specs 2. And so you see, like at the top, you have this producer and then macros, not surprising, taking more than 2 seconds to compile. And so you know that's, if you want to investigate, that's probably where you should get started. In this case, it might be absolutely okay. I'm just saying that Hydra gives you that as part of the output that it produces together with the class file. So today, it's good for developers, but maybe it's not as catchy as it could be. And what we're going to be doing is actually displaying this in a nice UI and not just giving you the compile time per compilation unit, but lots of other useful information that will help you, identify the problem. Yeah, the Scala Center is working on a profiling plugin that is going to be available soon. I know that Orge is working on that. But the main difference, I would say, is that Orge, I believe in, it's not available yet, so I don't want to say anything. But I think in a comment or something, he said that there is an overhead of 30 or 40%, something like around 30% every time you compile with that, like a compile time overhead. So it takes 30% more. And our goal is really that it takes not more, the overhead would be 1 or 2%. So I would say we're trying to focus on different problems, even though some of the statistics that they will report, we will also report. But one thing that they're missing, which to me is key, is this one. They don't show the compile time by compilation unit. Yeah, go and check. I'm 100% sure that's the case. Good. Thanks, everyone.